let's finish the proof of the proposition about the Galois homology that we had. Okay, so here is what we want to prove. So we have some field K, and we assume that field, and we assume that for any algebraic extension, the Brouwer group of L is 0, and then we want to bound homological dimension. So we know that for any torsion G module M, and G here is a Galois group of K sep over K. Homology of G with coefficients in M all equal to 0 when Q is greater or equal than 2. And the second assertion is that homology of G with coefficients in K sep star is equal to 0 when Q is greater or equal than 1. Okay, so let's see how to prove this. At the end of the last lecture, we observed that H2 of G with coefficients in mu L is 0. So here L is relatively prime to characteristic. And also, so if L is equal to characteristic, this group consists of one element. It's not very interesting, but we have a replacement for this. This group is also 0. And actually, we proved that this property holds for any field K of characteristic P, and you can replace 2 by any integer greater or equal than 2. Okay. So, and we are going to use sort of diversage to derive this assertion, first for Q equal 2, and then it will be a formal argument that it then automatically holds for any Q greater than 2. So, okay, so first of all, homology of pro-finite group commute with limits, filtered limits. So this is limit of homology groups. GMI. So, so recall that homology of a finite group itself is limit of homology of finite groups, right? Homology of finite groups can be computed explicitly by standard co-chain complex formed by functions on n copies of G. And then this assertion for finite groups, it's true on the nose, on the level of complices, right? Functions, for example, from G to this direct limit is the same as direct limit of functions. So it's again, this is not true if you consider G, if G were just an infinite group and you consider it abstractly, right? Functions, for example, homomorphisms from all homomorphisms from G to direct limit is not the same as direct limit of homomorphism from G to Mi, right? So it would not be true even for in degree 0. But because we consider continuous, well, for finite homology groups, it's okay. So, and this reduces, so this, we may assume that, M is actually torsion. M is torsion, so we may assume that M is finite. So M is finite, right? Because any module with continuous section of G is direct limit of finite modules, any torsion module. Now, so this is a finite abelian group, right? So it's skewed by some integer n, and by Chinese remainder theorem it can be. Да. Ну, здесь это, давайте я считаю, что я доказываю утверждение 1. То есть, да, я предполагаю, что это модуль кручения, хотя вот для этого утверждения это не важно. А здесь уже важно. Значит, читаем модуль кручения. Тоже. So M is skewed by some integer n, and by using the classification of, Chinese remainder theorem, you can write M as direct sum of L primary groups, right? Of groups skewed by some power of a prime number, right? So you may assume that it's skewed by a power of prime number. And moreover, you can filter M by groups which are skewed just by this prime number. So by diversage, we reduce to the case when L times M is equal to 0. L is prime. Right? Is it okay? So for example, suppose it's skewed by L squared. You just consider the subgroup skewed by L. The quotient is also skewed by L. Then you have a long exact sequence on the homology groups. If you know vanishing for of HQ for modules with this property, you also get the result for modules which are skewed by L squared. Okay? So that's the main assertion. So M is just as an abelian group. It's isomorphic to Z mod L to some power n. Okay. Now I will first give a proof in the case when Q is 2. And as I said, the general case will be reduced to this. And here is the argument. So Q is 2, case 1, Q is 2, and L is not equal to characteristic. Okay. Then we can do the following. We can, so suppose I have a class. Да. Мы, значит, к гомологии группы ГЛО с коэффициентами v Это, ну, у нас есть два определения. Есть, значит, мы вообще ими интересуемся, потому что это этальная когмология. И это значит этальная когмология спектра К с коэффициентами в m. m — это Галуа-модуль, который мы можем рассматривать как пучок здесь. По определению это xt в категории g-модулей, на которых g действует непрерывно. А непрерывно — это означает, что стабилизатор каждой точки открыт. И мы обсуждали, что это можно записать очень явно, выразить в терминах обычных. Здесь такие как бы непрерывные когомологии. Мы считаем xt, да, в категории не во всей категории g-модулей, а только тех, на которых g действует непрерывно. И это можно записать как предел по открытым подгруппам когомологии Q, G, фактор по H, ну, открытые и нормальные, MH. Вот. То, что G действует на M непрерывно, означает, что M является объединением инвариантов каждой. И это определение мы использовали вот здесь, чтобы доказать такое. Потому что вот такие группы G по H конечно, они заведомо коммутируются по бесконечными с пределами. Вот. Okay, so now so we pick some open normal H in G such that two properties called, first of all, every element of M is H invariant. We can do this because M is finite. And secondly, mu L is, well, these are groups of roots of unity in K SEP, but I want it to be H, they are all H invariant. So they belong to this finite extension corresponding to this subgroup. Okay. Now the trick is the following. Let's so I have G, H, and I will pick a larger subgroup, H prime. So I want to pick it in such a way that H prime modulo H, this is going to be a subgroup in G mod H, is a Silov L subgroup. Okay, and now I will explain how this method of trace works. Okay. So then, so we have second homology of G with coefficients in M. Okay. And first of all, it embeds into second homology of G with, of H prime with coefficients in the same M, right? So recall why it's true. So this is the same as homology of h of g with coefficients in induced representation. So we take M, this is a G module, I can consider it as an H prime module, and then, so here I can take the induction by Shapiro lemma. We had a geometric description of, well, geometric interpretation of this, but well, that's just the classical Shapiro lemma. And so the induced representation maps using, this is the trace map that we defined last time. So we have a map in this direction, and the composition of I and trace is multiplication by the order, so by the index of G in H prime. Right? That was the property of trace. So, and now H is a seal of L subgroup. So that means that this index is relatively prime to L. So in particular, it's invertible in M. Therefore, this is an injection, and therefore, this map is an embedding. This is one observation. The second observation is that M H prime is non-zero. Okay? And this is a very nice, well, exercise actually in linear algebra. So what we have here, we have M, and we have action of H prime modulo H. No, M is assumed to be stable under H. So in fact, this action factors through this group, and this is L torsion. So that means that it's a vector space over FL. Let me write. It's a vector space over FL, and this is L group, finite L group. So I claim that if I have any representation of an L group on a vector space over FL, then it has a fixed vector. So why is that? You prove it by induction. So any L group has a non-trivial center. So you can pick a normal subgroup here, which is isomorphic to Z mod LZ. So using induction, it suffices to show that if you have a representation of the group Z mod LZ on a vector space over FL, then it has a non-trivial invariant, non-zero invariant vector, right? So what is the group algebra FL of Z mod LZ? Well, by definition, this is polynomials in X modulo the relation x to the L power minus 1, but I can also write it as FL of X modulo x minus 1 to the Lth power. So in other words, given a representation of this group on a vector space over FL is the same as given an operator whose L power is 0, nilpotent operator. But any such operator has a non-trivial kernel, right? If it's nilpotent. Therefore, it means that so my M has an invariant vector under this subgroup. Now you take the set of all invariant factors under this subgroup. On this non-empty subrepresentation, I have action of the quotient of this L group by this normal central subgroup Z mod LZ, and then I use induction. Okay? So that's a basic fact about representations of L groups on L in characteristic L.
Would you say that any non-trivial orbit has to
Yes?
have a number of elements?
Yes. Yes. Mm-hmm. Okay. Good. So, and therefore, M has a subrepresentation R isomorphic to, well, a trivial subrepresentation. So this is embedding of this representations H prime modules. Yes? So, and this by my assumption, well, I know that H does not act on mu L, but it means also that H prime does not act on mu L, right? Because for the same reason, as a special case, this group, which is L group, cannot act on a one-dimensional space, non-trivially. So that means that this is the same as a Galar module, as H prime module is mu L. Mm-hmm. So therefore, we have we have a short exact sequence. So mu L goes to M and goes to M prime. That's the quotient. Second homology of H prime with coefficients in mu L is 0, right? Why is that? Just because, well, this was this observation, but it also holds, right? So here I use the fact that the Brauer group of K is 0, but also it's, since I know this for all finite extension, it's also true that H2 of H, say H. Что? Да, да, да. Ага. This is also 0. Да. Да. Ага. То же самое рассуждение. Ну, то есть это частный случай. Да. Okay. So, okay, so that's also true. Brauer group of L is 0 implies this. I need it for H prime, but just I decided that it's will be. Okay? So this is why it's sort of important to assume that we have not only vanishing of Brauer group of K, but also Brauer group of all finite extensions. So we know vanishing here. We know vanishing here by induction assumption. So I want to prove that this group is 0, and now I can argue by induction an order of M, right? So M prime has smaller order. So H2 of H prime with coefficients in M prime is also 0 by induction. No, just because it's the same argument. So you just replace, so if H is open normal subgroup, it corresponds to some finite field extension. Okay? And also, by the way, here we are proving a stronger statement that not only this group is 0, but also homology of H with coefficients in M is 0. But it amounts to replacing K.
Можно повторить аргумент, почему мы начали с того, что там должен быть тривиальный подмодуль, а потом закончили на том, что там должен быть μL?
Потому что μL изоморфен Z по LZ, как H прайм модуль. Потому что на корнях из единицы L-группа никак не может действовать.
Так мы так H' выберем.
Да. Угу. Мы сначала выбрали H, а потом здесь вот мы выбрали, где мы выбирали H? Вот здесь. Что H на корнях из единицы не действует, а значит и H. Okay, so that means that this group is 0, and we are done. Это, значит, вот как вот это. Это по индукции просто. M' имеет меньший размер. Да. Но если M' это 0, от H2 от μL это вот это вот утверждение. Да, это предположение. Угу. Хорошо? Okay, good. So now Q greater than 2, well, you use induction. So for any class alpha in Q of G with coefficients in M, there exists an embedding M into M prime such that under the image takes alpha to 0. So this is almost a formality. So if we worked with all modules, even continuous modules, I would just take an embed M into an injective module. So here we work only with torsion modules. So I have to be a little bit careful, but not so I may assume that alpha goes to 0. So how to check this? So I may assume that my alpha comes from some quotient M. So M is H invariant, and this comes. So alpha lives here, and then so I just embed it into HQ. Consider the map from this group to trivial group, and here I take the induction from G mod H, M, right? So that means that I can take for M prime the following. take induction from from H to G of M. So this group is 0. And so my class lives here, so going this way is the same as going this way, so I check this. Okay, so you have now M, you have M prime, and you have M double prime. And you look at the one exact sequence, and what you see is that each, what you see, yeah, so you have H Q minus 1 of G with coefficients in M. Double prime made into H Q of G with coefficients in M, and this goes to H Q of G with coefficients in M prime. So I have a class here, it dies here, but this group is 0 by induction. Good. So, so here I assume that the L is relatively prime to characteristic. Just the same argument with you replace mu L by Z mod LZ, by Z mod PZ, and use this fact. The rest does not change at all. Prove the same assertion for L equal to characteristic. And as I said, this part does not require any assumptions on K. So for a field of characteristic P, and any P torsion module, homology of the Galois group with coefficients in M vanish starting at degree 2.
Значит, мы для каждого класса альфа находим
M'.
Такое, что, значит, и H, такое, что диаграмма коммутативна.
Да.
Сейчас. А почему, значит, откуда мы получаем точную последовательность?
Нет, значит, вот мы тут доказываем, что для любой класс убивается, для любого класса альфа существует какое-то такое вложение, что вот образ здесь равен нулю.
Для этого мы находим такое H.
Да. Мы сначала находим такой H, а потом мы просто определяем M' по этой формуле. Okay, so that's okay with so we are done with the first step. Now the second, I won't say much here. So you so we proved 1. And now I claim that 1 implies that for any M, G module M, HQ of G with coefficients in M is 0 when Q is strictly greater than 2. So if M is torsion, then we have, then Q is actually greater or equal than 2, and here I need strict inequality. So, and it follows quite formally. So you just take M, and you consider M tensor Q. So this is a rational vector space. So for this, you know vanishing, no homology groups. And so here you have M torsion, and here you have some maybe M prime, which is also torsion. okay? This is torsion. So HQ of G with coefficients in M tor equal to HQ of G with coefficients in M prime, and it's also equal to HQ of G with coefficients in M tensor Q. These are all 0 when Q is greater than 1. And this, using, well, you split this into 2 short exact sequences, use 1 exact sequences, it formally implies this result. Okay. Потому что это рациональное векторное пространство, к гомологии конечной группы. В любом случае, это предел к гомологии конечной группы. Категория представлений конечной группы, рациональных представлений, она полупростая, никаких производных функторов там нет. Okay, so now if you look at this assertion, so we know vanishing for when Q is 2. That's the Brauer group. So, and for Q greater than 2, it follows from this general observation. Okay, so now let's, so we have the proposition, let's derive some, so let's see what we can get from this. So summary is that if we have a curve, so corollary that we need is that if X is a curve over algebraically closed field, then homology, well, let's say K is the field of rational functions. Homology, Galois homology of K sep over K with coefficients in K sep star, they're all equal to 0. Q greater than 0. Right? So because we proved Zen theorem last time, which is precisely what we need to apply the proposition. Okay, and now let's use it to compute a homology group of a Tal homology group of curves. So now let X be a smooth curve. Over algebraically closed field. I don't assume it to be proper at this moment. And then, some notations. I have generic point. And I have closed points. Closed points. And then the idea is to look at the, so I'm interested in homology of X. First, I will show that homology of X with coefficients in O star. They all vanish starting at degree 2. And for this, I look at the following short exact sequence. So let's take the sheaf of invertible functions on X. Let's take its, let's say eta. So I look at the invertible functions on eta, right? This is just that's a Tal sheaf on a spectrum of a field. And this is the multiplicative group. And I take J O star of that. So I I take a sheaf on the generic point and I extend it. So you may think of this as functions, non-zero meromorphic functions on X. So here I have regular functions. I have an embedding, and what is the quotient? Well, so if you have a non-zero rational function on X, you can look at its divisor, and if the divisor is 0, then it's actually regular, right? So I claim that this is sum over all closed points of I, X, low star of constant sheaf. This is the divisor. And of course, locally, so this is a sequence of sheaves for a Tal topology. And locally, well, this map is surjective because locally, every divisor is principal. That's true even Zariski locally, but I needed Tal. So now I'll need a lemma. This functor is J lowest. Well, these are closet embeddings, so these are finite morphisms, so there are no higher direct images. This is not a finite morphism. It's rather look like an embedding of an open set to X. So the claim is that higher direct images vanish. Go to 0 when Q is greater than 0. Okay? So let's prove this. So proof. So, okay. So what do we have to show? So RQ J O star of O star. So I need to show that, well, the stalk at the generic point is clearly 0. So I need to show that for any geometric point which is over closed point X, this stalk is 0. So, and what is it? So I want to show vanishing of this. That's by definition. We discussed how you compute the derived. So I will draw a picture here. So this is my curve. Think of eta as kind of, it's a good approximation. It's a small open subset, but anyway, it's dense in X. So, and you have a point. So in order to compute this, you have to take a generalization of a very small neighborhood of point x, so generalization, and compute homology of this sheaf over punctured disk, right? That's how you compute the derived direct images under an open embedding. So I will write formally what it means. So it's HQ of eta. Eta is a scheme over x times spec of generalization. Strict generalization, well, so x is a, I don't need to write bar if you wish. It's because my field is algebraically closed, so this is just x. Or eta. So think of this guy geometrically as a kind of punctured disk, very small punctured disk. It's a tall analog of a punctured disk in classical topology. So homology of higher direct image is precisely, this RQ is precisely homology of your sheaf over this punctured disk. I want to show the vanishing. Well, we discussed what the generalization is, right? So this is generalization index. So this generalization is a subring of the ring of Laurent series, right, of the completion, which are algebraic over capital K. So power series which are algebraic over K. So here you take this standard product. So and eta is the spectrum of this field. So that's just the fraction field of this generalization. A fraction field is an algebraic extension. This is equal to spec L, where L is an algebraic extension. Okay, of K. Again, this is Laurent series, which are Taylor series, which are algebraic over K. So when you take, when you tensor it with K itself, you get a field which is an algebraic extension of K. And so this is the nothing else but homology of Galois group of L sep over L with coefficients in L sep star, and we know the vanishing. So where is it? It was a corollary of this. Yeah, so you just replace K by L. It's an algebraic extension. So this is 0. So what it means that corollary of this is that homology of this sheaf is the same as, of my curve x with coefficients in the sheaf is the same as homology of eta. So eta with coefficients, I will write it as Galois homology of K sep, okay, with coefficients in K sep star. And so I know that this is 0 when q is greater than 0. All right? Is it okay? So, so here is a maybe an explanation. Yeah, this is called, well, it's a formal argument, which is but since we haven't discussed it yet, so let me explain. So you have.
Сейчас, вот эту точную расстоянность мы нигде не использовали. Если использовали.
Пока не использовали. Пока не используем. Мы сейчас скомбинируем вот это утверждение с той точной последовательности и получим то, что нам надо. Но давайте посмотрим, откуда это следует. То вообще, допустим... Okay, so you have two functors. So you have sheaves. Suppose you have just in general a morphism of schemes from x to y. Let's call it f. Then you have sheaves on x. You have sheaves on y, and you have global function, a global section functor. This is abelian groups, right? And this is the derived direct image. Well, this is just direct image. Okay? So the composition of these two functors, these are global sections on y, the composition is global sections on x. That's clear. Now I claim that the same is true when you consider the derived categories here. And replace every functor here by derived functor. So why that? Well, strictly speaking, to make it, I need to put plus here. So plus means that I consider the derived category of bounded from below complexes. So why that? So every element here can be represented by a complex of injective objects. So the point is that this functor FO star takes an injective sheaf on x to an injective sheaf on y. And that follows from the fact that FO star has a left adjoint, which is exact. Инъективный. Мне кажется, так. So in order to compute this composition here, what you do, you replace your complex by a complex of injective, and then you apply first term-wise FO star. You still get a complex of injective. So to compute this, you apply gamma term-wise, but that's the same as this functor. So that means that once you know that injective object goes to injective objects under first functor, it follows formally that the composition of the derived functors is derived functor of the composition. That's yields to what's called Grothendieck-Larrey spectral sequence. And the way you apply it is the following. Well, this is equal to R Q gamma of x with coefficients in this higher guys. All right? So this is true because of the lemma, right? Because this complex is a cyclic in all degrees other than 0. So this equality is non-trivial. It's content of the lemma. But so once you have this equality, this is equal to h q of eta with coefficients in O star. And that's the Grothendieck-Larrey spectral sequence. Well, I won't use spectral sequences much, so this is kind of for proven results. This is more useful than spectral sequences for actually if you want. Вот это, да? Вот это. Вот это. Значит, я объясняю, как следует следствие. Значит, во-первых, у меня имеется вот это равенство. Почему? Потому что вот этот комплекс, он ацикличен во всех степенях выше нуля. Это вот лемма. Значит, а в степени 0 это вот это. Если комплекс ацикличен, имеет к гомологии только в одном месте, он просто изоморфен. Вот. Ну, это вот это вот рассуждение. Да? Почему? Потому что я здесь беру, вот что я тут считаю? Я сначала прошел сюда, а потом посчитал RQ от гамма. Но это то же самое, что взять просто R. Да. Да. Very good. So I think I will not use this proposition anymore. And now we combine. So now let's look at the finally. So what we get from this is that so corollary. So H1 HQ of x with coefficients in or x star vanish in all degrees greater than 0. Greater than 1. Greater than 1. Okay? So why that? So proof. You just use one exact sequence associated to this, and you observe that homology of x with coefficients in I x star of zx. Well, this is a finite morphism. So this is homology of spec K with constant coefficients. And this is algebraically closed. So it's 0 when Q is greater than 0. So combining this argument, this corollary, right? So you know vanishing of higher homology groups for this, and therefore you get vanishing, this vanishing. And H1, well, you take global sections here, so we recover the result that we actually already know by faithfully flat descent. H1 of x with coefficients in O star is peak x. Okay? So, and another corollary. No. What is L? There is no L here so far. But now I will have L. Just as an abelian group, right. It's a group. So, but now I will use, well, that's, so suppose I have L, which is relatively prime to characteristic of K. Then, and let's say first X is smooth projective. Then, what we have? H0. So I'm interested in homology of, yeah, L here is any number. Maybe, sorry, maybe I should say A. It's not necessarily prime number. HQ of X with coefficients in mu n. So I claim that this is mu n of K, so just group of roots of unity here, right? This is non-canonically isomorphic to Z mod and Z. So when Q is 0, it's torsion and torsion elements. When Q is 1, it's Z mod and Z when Q is 2, and 0 otherwise. 0 otherwise. So, well, this is the sheaf of roots of unity, right? So another name for this that we had was Z mod and Z twisted by 1. That's just notation. As a sheaf, if my base field has roots of unity, my field K is algebraically closed, then this sheaf is non-canonically isomorphic to Z mod and Z. It's just a constant sheaf. This twist does not do anything. When your field is not algebraically closed, then it's a different. So, and how does it follow? Well, you have, first of all, you use Kummer exact sequence. O star X goes to O star X. This is exact for Étale topology. And so you write lone exact sequence of homology groups, and the only non-trivial statement, right, you use vanishing, that the previous corollary. So only H1 of these guys survive. So, and the only non-trivial statement is that, so if you take this quotient, then this is Z mod and Z, right? So, how does it follow? Well, here I will, the best argument uses some, the Picard scheme. So for a curve, you have, so this is the group of K points of the Picard scheme of X. And the Picard scheme of X is a group scheme that whose connected component, neutral connected component, is called pic 0. And this is an abelian variety. And the quotient, well, this is the degree map, is Z. So because my field is algebraically closed, it follows that the same is true for, So if you just consider k points of this guy, you still have the same exact sequence. And so this is an abelian variety. And for every abelian variety, the map from peak 0 x, well, from this abelian variety to itself, multiplication by an integer, any integer, on an abelian variety is an isogeny. It's surjective. And because my field is algebraically closed, this map remains surjective when I consider k points. Right? If you have surjective map of schemes, it's surjective on k points. On k is algebraically closed. And therefore, that means that this peak 0 is divisible group. Every multiplication by any integer n is surjective. Therefore, it does not contribute to this quotient. Peak x, you can write peak x as peak 0 of x times z. But because peak 0 of x modulo n is 0, you get this result. OK? So we computed a Tal homology of curves with constant coefficients. Oh, sorry, maybe let me, as an illustration, another illustration for the Larrea spectral sequence, do one more computation. So we computed homology of smooth projective curves, right? And by the way, peak x and torsion points is non-canonically. This is the kernel of this map. So this is an abelian variety. So this is multiplication by n. So this multiplication by n is an isogeny of degree n to the power 2g, where 2g is where g is the dimension of your abelian variety. So in the case when n is relatively prime to characteristic, this map is also a Tal, because its differential is multiplication by n, and n is invertible. So that means that the kernel of this map on k points consists of, well, it's z mod. Well, I think we discussed this once. So this is 2g. OK? Good. So non-canonically, it's isomorphic to this. Now, suppose my x is now not smooth curve, so smooth curve, but not proper. So let's embed it into its compactification. So, and I say that, let's say that x minus x consists of some, well, points, x1, xr. Ну, смотрите, значит, во-первых, следует утверждение про порядок этой группы. Да, потому что вот степень этого, степень, degree, is equal to n to the power 2 times dimension. This is an abelian variety of dimension g, where g is the genus. So because this map is Tal, it follows that its kernel has this size. Size means that it's n to the power 2g. But now, using divisibility argument, you can show that this is actually isomorphic as an abstract group, right? So So what do you, it's formal. So for example, how you, suppose n is equal to p squared. So what do you know about this group? P squared torsion in an abelian variety. You know that it's a group of the desired order, and you want to show that it's precisely z mod p squared to 2g. So there are several groups of this order, right? So what do you need to show? You just use the fact that p torsion points on your abelian variety is z mod pz to the 2g. If it were something else, then p torsion would be larger. Okay. So, so what do I want to say here? So let's call this map J. And so I want to compute homology of X. So how to do this? So let's take again our exact sequence. This is O star X. O star X. And let's apply, let's take J O star of this. So I will have J O star of mu n. I will have J O star of OX. I have J O star. That's multiplication by n. So this need not be, this functor is not exact. So I'll have R1 JO star of mu n. And then I have R1 JO star of OX star, and so on. So what do I know about this? So I just take this short exact sequence of sheaves on X, and I take the direct image to X bar. So we already proved that this guy is 0. We use, that was the, we consider the direct image from generic point, but the stocks here are exactly the same. No difference. So what is, remember, so this OX, Q, X is the same. It's just homology of X times spec gensalization this is X over X bar. So that's still the same field. That's a, so that's a field, right? This is a local ring whose maximal ideal is the precise the closed point of X, closed point of X bar. When you base change, you will not have any, well, there will be no non-zero ideals. It's a field. So we know that this is 0. So all these groups are 0. This is 0 when Q is greater than 0. Что? Пучок обратимых функций здесь. Okay. So from this, we conclude that mu n has only first, may have only first non-zero derived direct image. Yes? We have a short exact sequence. So what is the co-kernel of this map? Let's compute this. So we look at invertible functions on well, sort of rational functions on x bar, which are invertible on x. Model of functions, model multiplication by n.
Well, one thing that exists here is that there are functions who have poles in xi of order not divisible by n.
Yes, and there is nothing else. So if you have a function whose order of pole is divisible by n, then locally you can extract a root. It's a Natal cover. So that means that the co-kernel of this map is going to be direct sum over I equal 1 n. M equal 1 n. And here you will have I m x m star of the constant sheaf. Okay? Model M. Model M. So the map here is the following. You take this function and you take its divisor. Its divisor lives here. But if its divisor divisible by n, then you can extract a root. Good. So, so we computed. Now let's use it. So I want to use so R gamma of x with coefficients in mu n is the same as R gamma of x bar with coefficients in R j O star of mu n. That's a special case of that assertion about the derived categories. Now, what do we know about this complex? So we know that it has homology in 2 degrees, in degree 0 and in degree 1, and nothing else. So homology in degree 0 gives me a map from mu n itself to this complex, right? So if you have any complex that has homology in degree 0 and 1, you have a map in the derived category from its 0 homology, view it as a complex, to this guy, right? And then the cone of this map is what we had over there. Its first homology, m equal 1 n j x m rho star of z x m modulo n. Good. So this is not this is kind of what's called a distinguished triangle in the derived category, right? So if you have a complex with 2 homology groups, first of all, it's quasi-isomorphic to a complex of length 2. There is a truncation, left truncation, right truncation, which gives you quasi-isomorphism. And then you have H0, so kernel of alpha. That's a map of complexes. And then you have co-kernel of alpha. It's also a map of complexes. So you have a short exact sequence of complexes, and short exact sequence of complexes gives rise to distinguished triangle in the right category. That's how they defined. So yeah, and by the way, no one corrected me. This is a very important correction. This is -1, right? This complex sits in degree -1. Oh, in degree 1, which means that I should put -1 here. This is a distinguished triangle. So mu n twisted by 1. Okay. And now every distinguished triangle gives rise to lone exact sequence of R gamma. So it goes under the right functor to a distinguished triangle. So you take this triangle and you apply R gamma. You get still R gamma X bar. Okay. So, and what you find from this is that, so let's look now. So this is again still a short, now this is a short exact, well, this is a distinguished triangle in the derived category of abelian groups. It gives a lone exact sequence of homology groups. So I'm interested in homology, mostly in homology in degree 1, because in all other degrees they're trivial. So let's say that H1 of this is x mu n. So here I will have H1 of x bar mu n. That's something that we already computed here. So this guy has no homology in degree, well, it has homology only in 1 degree. So this sheaf, right, it has trivial higher homology groups. I shifted by -1, so it means that this guy sits in degree 1. So that means that this map is injective, right, from the lone exact sequence. And so now I have homology of this guy in degree 1, so this is direct sum of z mod and z over all I equal m equal 1 n. Yeah, R. Good. Yeah. And now I still have the boundary map, which goes to H2 of this. And the boundary, so by the computation that we just made, this is z mod and z. And now the next term, which is the next term is already 0, right? And so I get short exact sequence. So why is it the next term? Is why is it so? Yeah, so I claim that it's 0. Let's try to see this. Okay, so 1 second. So. Okay. Thank you. So here is the reason why. So why is it 0? So I need to know that H2 of x with coefficients in mu n is 0. That's I need to know. And this is why the computation that we made here, by this computation and the Kummer exact sequence, this is still peak x modulo n peak x. Thank you. Right? But x now is not proper, right? So so you have peak x bar. It maps to peak x, right? So so remember that we have a short exact sequence. This is an open curve. This is a closed curve. That's the restriction map. There is a short exact sequence. So where this map takes a combination of integers to the divisor supported at xi. And so here I have peak 0 of x bar. So this map is surjective, but I claim that even this map is surjective. Why is that? Because so I claim that so every line bundle on x can be extended to a line bundle on x bar. But I have some freedom. I can add any combination of these points. So I can make this line bundle on x bar to have degree 0. So that means that every line bundle on x can be extended to a degree 0 line bundle on x bar. But this group is divisible. So that means that this is 0. And that means that this is 0. So you have surjectivity here. Thank you, Stepan, for catching. So higher homology groups of this for fine curves vanish. And here you have this exact sequence, so you have some residues map and the residue theorem saying that the sum of residues is 0. Okay, I'll stop here.
Can we do all that for spec Z and spec OK for K number?
It's more complicated because the Brauer group of the field of rational functions, namely the Brauer group, which will be Brauer group of Q in this case, is not equal to 0. So the first thing that you want to do here is to consider curves over a non-algebraically closed field. In general, this is still kind of complicated, though you can use Larrey spectral sequence argument. You can first take a map from X to spec K, and then take a homology on spec K. But in general, it's complicated. But if you do it over a finite field, then using Length's theorem, you can kind of just from the computation that we made, you can rederive the basic statements in class field theory for functional fields. For example, you can compute the Brauer group of that field, show that it's equal to the direct sum of Q mod Z, where summation is taken over closed points with the condition that the sum of this residues is 0. So for number fields, the difficult thing will be to show, for example, vanishing of RJO star of O. That's this computation is the main step in the classical proof of computation of the Brauer group of local fields.
There is no X bar.
Yeah. Yes. So there will be okay. And so what?
You mean J over star as what? Embedding of step K
So what do you want to prove? You want to compute, for example, homology of mu n. First problem is that mu n is not quite it's not an étale sheaf on spec z. You have some problems over prime numbers which divide n. So maybe first thing that you can do, you can try to compute the Brauer group of the scheme spec z. So homology, étale homology of spec z with coefficients in O star. This is a very reasonable question. So here we did this computation. What do you get when you compute? So what is the Brauer group of spec z?
So it's in a group in classes of division algebras which are
Everywhere split. And what is this?
nothing, I guess.
Nothing, because the Brauer group of Q is, is direct sum of Q mod Z and Z mod to Z corresponding to the infinite place, and with the condition that the sum of all these residues is equal to 0 if your division algebra over, if your class over spec Q extends to an algebra over actually spec Z, it means that all the residues at prime numbers are equal to 0. Using the fact that the sum of residues is 0, you also know that the class at infinity is 0, and then you're done. So I don't know how you can rederive this computation for spec Z or for spec Z with several primes removed from using this technique. I don't think that it's possible. But so the key will be some, yeah. But for curves you can do this, for curves or a finite field, and you can rederive. All class field theory statements using that notion.
The analogs of these results for spec Z, they are known and they are equivalent to Pascal's.
Yes, yes. But this is, again, it's more complicated because it's rather analog of these results for curves over a non-algebraically closed field, like FP. Yeah. Okay. Что? Ну вот там, по-моему, где-то объясняется как раз, как изучая кривую Фонтена-Фарга, вычислить группу Брауэра. Купе, правда?
Ну да, купе.
Да. Но это не самое короткое доказательство. Но не самое короткое доказательство получается.